Okay, so I'm going to talk about today a joint work with Misson Dupuis and Clément Guillot. So Clément is somewhere in the room, he's here. And he's going to present a poster with more details about what I'm going to talk about today on Thursday. So if you are interested in having more details about this work, you can go and see him and ask him all the questions you want. And actually our aim in this work was to find a new variational principle for the solution of the time-dependent Schrödinger equation. So our motivation stems from electronic structure calculations. I'm going to explain this more in details, okay? And the problem with this time-dependent Schrödinger equation is that when you are dealing with a systems with a large number of electrons, you have to deal with very high-dimensional problems to solve. And this new variational principle, it has quite a lot of nice features when it comes to building approximations with, of low complexity of the solution of the time-dependent Schrödinger equation in high dimension. And so that's what I would like to tell you about today. And of course, if you've got any questions, don't hesitate to interrupt me and ask them. So first, let me start with the motivation of this work, why we were interested in building this new variational principle. And first, let me introduce you the type of Schrödinger equations that we are really interested in, okay? So here, what we are after are numerical methods in order to compute the electronic structure of molecules, okay? So you have to think about molecules through these pictures, okay? These guys are composed of nuclei. Nuclei are quite heavy particles composed of neutrons of protons. And at this scale, you can consider them as being classical point particles that are described by their positions and their electric charges. However, and you have in addition some electrons that act like a gluing cloud of the molecule, okay? But at this scale, you cannot model them as point particles anymore. You have to model them using quantum physics. And so you cannot represent the state by just positions and velocities of the electrons. This is not possible. And you have to use quantum mechanics in order to understand what's happening for the electrons inside the molecules. And it's important to understand the state of these electrons because they account for many of the fundamental properties of a molecule, say electrical, chemical properties, or magnetical properties. So let me first introduce you the models that we are really after here, okay? So the approximations that I told you, in the sense that the nuclei can be considered as point particles, it is called the Born-Oppenheimer approximation. So Oppenheimer is the guy from the movie, so that's the same guy, okay? And Born was one of his friends, okay? And so here, just need to fix the notation. I'm going to assume that in the molecule that we are interested in, there are M nuclei, okay? So imagine for the H2O molecule, you've got 3 nuclei, 2 hydrogen and 1 oxygen, okay? And so, in general, I will have m of them in the molecule I'm interested in, and the positions of the nuclei will be denoted by R1 up to Rm. These are vectors of R3, okay? And the electric charges of each of the nuclei are denoted by Z1 up to Zn, okay? That's for the nuclei. And now, in addition, you have got n electrons in the systems. So, as I told you, at the scale, you have to consider them as quantum particles and not as classical particles anymore. And so the state at time t, okay, will be described by the so-called wave function, okay? This guy will be denoted by psi of t in the rest of the talk. And this wave function, which describes the state of the electrons at time t, is a function defined on R3n with complex values, okay? And so its physical interpretation is the following, okay? If you look at the squared modulus of this wave function psi of t evaluated at x1 up to xn, where x1 up to xn are vectors of R3, this guy represents the probability density of finding at time t the n electrons in the positions x1 up to xn respectively, okay? And so this physical probabilistic interpretation has the following consequence, which is the following. If you consider subdomain B of R3n, and you integrate over B the modulus squared of the wave function at time t, this gives you the probability that the electrons will be located in the set B at time t. Okay? And in particular, if you take B equal to the whole space R free n, then this integral will be equal to 1. Okay. So now the evolution of the state of the electrons within the molecule is given as the solution of the time-dependent Schrödinger equation, which reads as follows. So here, you've got this equation here. So I dt psi of t minus h psi of t is equal to 0. And you've got here an initial condition for the wave function. Okay. And h here is an operator which acts on square integrable functions. Sorry, I forgot to mention that. Of course, since we've got this probabilistic interpretation, it means that psi of t is a square integrable function over R free n. Okay. And what is h more precisely? This guy is an operator which is called the Hamiltonian of the electronic system. And it's composed of two parts. Okay. So here, h, this operator, is the sum of a part which I will denote by h0 plus another one which I will denote by a. Okay. And I'm going to give the definitions of h0 and a just now. Okay. And you've got here a first contribution, h0, which is just the minus Laplace operator, acting here on all the variables x1 up to xn. So it's a Laplace operator on R free n. Okay. And here, a is a multiplication operator by a potential function v, which depends on x1 up to xn. Okay. Which writes as follows. And these two different parts have two different physical meaning. Okay. This first operator, the Laplace operator, corresponds to the part of the energy of the system of electrons linked to the kinetic energy. And this part here is related to the Coulombic energy of the electrons. And here you see there are two different terms in this potential V. There is a first term where you've got the charges and the positions of the nuclei that appear. This is the term corresponding to the Coulombic energy between the electrons and the nuclei. Okay. And you've got another term here, which takes into account all the different pairs of electrons here. And this term here takes into account the Coulombic energies of electrons within themselves. Okay. So the time-dependent Schrödinger equations reads as follows. And again, here h is an operator acting on functions of L2 var free n, which is a sum of two different parts. This Laplace operator plus a multiplication operator by this potential. Okay. Of course, when n is large, this leads to a very high dimensional problem. Okay, when n, the number of electrons is large. And so you cannot use traditional numerical methods to tackle it because you will have the curse of dimensionality right into your face. Okay. You have to think that n in molecules, for instance, the H2O molecule, it's already 10 electrons. And for more complicated molecules, it can be even worse. Okay. So what do people do in order to try to compute approximations of the solution of this Schrödinger equation in practice? Well, in practice, there are a huge zoology of methods used by quantum chemists, okay? But most of them can be written as follows, okay? Most of them uses some subset sigma of the set of square integrable function defined on R free n. And this subset sigma is a subset of functions of x1 up to xn that can be described with a low complexity. I'm going to give some examples right now, okay, some precise examples. There are various choices for such low complexity functions set, okay? One of the most popular methods used by quantum chemists is the use of low-rank tensor formats, okay? So I'm not going to give you all the different low-rank tensor formats that exist in the world. I'm going to spare you with the different formulas. One very simple such subset of low complexity functions is the set of pure tensor product functions. So more precisely, you can consider as a low complexity subset of function sigma among all the squared integrable functions of R free n. You can only consider the ones that can be written as a product of univariate functions, okay? So such that this function can read like a product R1, function R1 of x1, times Rn of xn, okay? Where R1 up to Rn are just squared integrable functions of R3, okay? So of course, this is a very small subset of all the functions of L2 over 3n, of course. But when it comes to numerical discretization, representing a set of n functions depending on just one variable in R3 each is much, much lower than representing a full function defined on the the full half-Riemann space. Okay? So that's the reason why representing such a set of functions has a much, much lower complexity than representing any function in L2 over 3n. Okay? So this is just a very simple low complexity subset. In practice, people use more complex subsets which have better approximation power. And for instance, quantum chemists used Tucker format. So in their language, that's what they call multi-configuration self-consistent field. Okay. So these are just for those of you who are aware of these formats. I'm not giving the full formula here. And you can also use some concentrate format or hierarchical tree format. So these are, let's say, I'm not giving the precise definitions here, but these guys, these are low complexity, these are subset of functions which can be represented with low complexity that are more complicated than this one, okay? But for the sake of this talk, it's enough for me that if you take this type of example just to fix the idea, okay? There is also another very popular type of low complexity functions that are used in these settings. And these are linear combinations of Gaussian functions. Quantum chemists like them a lot because with Gaussian functions, you can make a lot of computations with this Schrödinger operator very explicit. And so things can be computed very easily, okay? So I'm just giving a few names of people working in this field. The list is far from being exhaustive here. And here, what people are after, once they have chosen a subset of low complexity functions, sigma, they want to compute an approximation of the exact solution of the Schrödinger equation psi, which will be denoted in the talk by psi tilde. And this approximation will be constructed one way or another, such that for all time t, psi tilde of t will belong to the subset of functions with low complexity. Okay? And there are various ways to compute such approximation which satisfy this property here. Of course, one would like this approximation to be an approximation of the exact solution as accurate as possible, naturally. Okay? So let me now explain to you the classical way people compute this low complexity dynamical approximation. The classical way these are computed is called the Dirac-Frenkel variational principle. So let me explain what this is about and what are the drawbacks of this variational principle. Okay. So here I'm just using some notation. So the set calligraphic H here, the notation here, will refer to L2 over 3n. So it's a space of functions my time-dependent wave functions belong to. Okay. And these guys are just a scalar product and the norm of this Hilbert space. Okay. So what is this Dirac-Frenkel variational principle? I'm writing it here on the formal level. So take sigma, your subset of low complexity functions, and assume for a moment that this guy is a regular submanifold of H. So that in particular, at any point belonging to sigma, you can define the tangent space to sigma at this particular point. Okay. Then let me draw a picture. Okay. You have to think. Ah, pardon, excuse-moi. J'ai pas réfléchi. You have to think of sigma here as being a regular manifold, which is a subset of L2 over 3n, the full functional space. Okay. And one wants to compute an approximate dynamics psi tilde, such that psi tilde of t always belongs to this manifold sigma. Okay. So if you compute just a dynamical approximation, you don't have the choice. If you look at the time derivative of such a psi tilde of t, this guy has to belong to the tangent space to sigma at the point psi tilde of t. So there is no choice, okay? And now remember, the exact time-dependent Schrödinger equation, okay? If at time t, you have an approximation given by psi tilde of t, a natural way to define potential value of the time derivative of psi tilde is to define it as an element of the tangential space to sigma at the point psi tilde of t, which is as close as possible to the term appearing in the equation. And here this guy is minus I h psi tilde of t, okay? And here you want this guy to be as close as possible to this guy, here, for instance, in the L2 over 3n norm, okay? So that's, at the formal level, that's the Dirac-Frenkel variational principle. So it's a time machine scheme where at each time you're building this approximate dynamics by choosing its time derivative to be as close as possible to this term which comes from the original PDE that you want to approximate. Okay. And so this is on the formal level. So this is just the first order optimality condition that you obtain if you solve this minimization problem here. Okay. This comes just from the fact that dt psi tilde of t is chosen as the solution of this minimization problem here. Okay. However, so this is nice in the case when sigma is a very regular manifold of the set of functions of L2 over 3n. But the problem is that in general, the low complexity sets sigma, which are used in practice, are not regular everywhere. Okay? And so sometimes this tangential space may not be defined, okay? And this might yield some difficulties, okay? And in particular, this has the consequence that if you study this type of approximate dynamics given by this Dirac-Frenkel variational principle, when you study it from a mathematical point of view, in general, one can only prove the existence under some assumptions of a dynamics only locally in time, for small values on time. And in general, also, the value of the time interval on which you can define such a dynamics is not explicitly known. Okay. You can characterize it if you use some given low rank formats and so on. And there are lots of work in particular by these people here. And I forgot a lot of the names there. But in general, you cannot have, for these low complexity sets, global existence in times, because you've got a lack of regularity of this, of the practical set sigma. Okay. So here, what we tried to do was to propose another variational principle in order to build low complexity dynamical approximation for this time-dependent Schrödinger equation, based on another principle, another idea, another ways of seeing things. Okay. So here, let me just explain to you in a nutshell what we were after. Here, our aim is the following. The exact solution of the time-dependent Schrödinger equation, we want to reformulate it as the solution of a standard Lax-Milgram problem under the following form, where xh will be some Hilbert space of functions that I'm going to detail afterwards, okay? A will be a continuous Hermitian cohesive sesquilinear form defined on xh times xh, and B is a continuous linear form from xh to C. So we see this guy is simply a Lax-Milgram problem, okay? And this Hilbert space here will be a Hilbert space of functions depending on time and on the space variables x1 and 2, xn. Okay. And so you will have all the standard properties of a Lax-Milgram problem in the sense that the psi, the exact solution of the time-dependent Schrödinger equation, will be the solution of a minimization problems of the form here, where E of phi is a functional defined on this Hilbert space xh, which we'll write as follows, okay? Very classically, okay? So keep in mind, the xh is a set of time-dependent and space-dependent functions. Actually, There are several ways to do so with the time-dependent Schrödinger equation. There is no such unique representation, and there will be one that will be more convenient for us in order to build dynamical low complexity approximations of psi using either low-rank tensor formats or Gaussian functions. That's our aim here. Okay, and so what is the wish list that we would like for such a variational formulation? First of all, the Hilbert space of time and space dependent function should be easy to characterize. I should give you a definition. Okay, xh is that. Okay. The coercivity and continuity constants of the bilinear forms A and B should not depend too strongly on the value of the final time t. We want the conditioning of the problem to be relatively mild when we've got long-time dynamics. Okay. And also, we want the formulation to be convenient, as I told you, with low-rank tensor formats or with Gaussian functions to build these low-complexity dynamical approximations. Okay, and so this is then to build afterwards an alternative variational principle to the Dirac-Frenkel variational principle. Okay, and in particular, I'm a bit anticipating. This new variational principle will have some good properties. First, it will enable to define dynamical low complexity approximations over the whole time interval 0t, whatever the value of big T. And in addition, thanks to the variational principle, we have certified a posteriori error estimator, a bit free. So we will be able to quantify the error between the dynamical low complexity approximation and the solution of the exact solution of the Schrödinger equation. Okay. So now the next two parts of my talk will be dedicated to the construction of this new variational formulation. Okay. And then in the fourth part of my talk, I will tell you how we use that in order to build another dynamical low complexity approximation. Okay. And then I will sum up. Okay. So now let me drive you through this new variational formulation. So here I need to take a step backwards in terms of level of abstraction. Okay, so bear with me, sorry for that. Here now, calligraphic H will be a general Hilbert space. Keep in mind that later it will be again L2 over 3n. Okay. H here is a self-adjoint operator on big calligraphic H with some domain. Okay. This will be the Schrödinger operators that I've introduced before. Okay. And I'm also going to denote by I the time interval 0t. Okay. And in particular, I will make the use of this notation for the Bochner space, L2 of I, H. And these guys are time-dependent functions with values in H that are squared integrable in time. Okay. Okay. I need to introduce some other notation. Sorry for that. Here's the notation as the following. I'm going to consider U0 an element in calligraphic H, which will be an initial condition to the Schrödinger problem. And F here will belong to this Bochner space and will be a right-hand side to the Schrödinger equation. So this guy, I didn't have it in the original problem, but I will need to explain to you how we build the variational principle. Okay. And for a given U0 and a given F, I will denote by U star the unique quick solution to this time-dependent Schrödinger equation with initial condition U0 and right-hand side F. Okay? So there is a precise way to define this notion of weak solutions. I'm going quick here, believe me. Okay. And now let me begin with the first variational formulation, but which is not useful for what we want to do. One first try can be the following. Let me define first xh, a set of time and space dependent functions, which will be the set of function U star in the Bochner space, such that there exists some initial condition and some right-hand side F, such that U star is solution to the Schrödinger equation. Okay, this is a complicated set, and in particular, I don't know how to characterize it in an explicit way. Okay, but it has the advantage of existing. This guy, you can prove it that it is a Hilbert space when you embed it with a natural scalar product, and you have a natural associated norm, which results follows, okay? And the associated norm, in particular, you can see it's equal to the sum of the initial value of a function u in xh plus a term related to the to a norm of the residual of the Schrödinger equation in the Bochner space. Okay. And so you can prove that the solution of the time-dependent Schrödinger equation is the solution of this type of minimization problem over all possible function u in this space xh. Okay, very well, but it's not useful precisely because of what I told you in the beginning. I don't know how to characterize this space xh. So we have to do something else. So actually, when I told you that we don't know how to characterize it, I'm a bit lying. We can give some characterization which are not very useful for very practical and very handy. Actually, what you can prove is that this set xh, you can represent it as follows. It is also equal to the set of functions that are given under the following form. So here you see this is the semi-group associated to the operator h, exponential minus ith, times some function v, and v here is h1 in time with values in the calligraphic h space. Okay? So there is some way to have a slightly better characterization of this space. But here we have made some progress, but it's not very useful yet, because this semi-group here is not easy to compute or characterize in general. Okay. So, overtry. The overtry now, it relies on the fact that the operator h appearing in the electronic structure calculation introduced to you before can be written as a sum of two parts, as I've told you. Okay. So in the electronic structure calculation problems that I've presented you, I wrote h, the full operator, as a sum of h0, which was the Laplace operator, and a, which was a multiplication operator associated to the Coulomb potential v that I've given you before. Okay? And now that's what we are going to use in order to propose a new variational formulation that will be more handy to use. So indeed, the space xh0 will be easily characterized. I'm going to tell you that afterwards. And this will come from the fact that a is a multiplication operator can be seen as a small perturbation of the h0 of the Laplacian operator in some sense. Okay. So that's exactly what I told you. h0 will be the Laplace operator. And then the proof of the following results will rely on the so-called Kato smoothing theory. Okay. So I'm not going to go into details into this theory. I'm just going to give you the main tools that we use in order to get to this new variational formulation. Okay. So here, everything works because actually, if you take A again to be the multiplication operator by the Coulomb potential and H0 being the Laplace operator in the electronic Schrödinger problem, everything works because actually you can prove that these operators satisfy such a condition. Okay, I'm not detailing it. But then, since you've got that, you've got a very nice property, which is that the space xh that I've introduced to you before, it is equal to the same space where you use only the operator h0 instead of the full operator h. Okay. So the space I've given you, so remember, sorry, puff, I'm going back. Boom, boom, boom. That was this space, okay. And this space actually is exactly the same where if you put h0 only the Laplace operator here instead of the full operator minus Laplace plus the multiplication operator. Okay, that's the first thing. And the second thing is that the norm of the space xh that I've introduced before is equivalent to the norm in the space xh0. And you've got constants here that depends quite mainly on t, the finite time. Okay. So only here this guy only decays algebraically with t, and this guy only grows linearly with t. Okay. And so, if you do so, the solution u star of the Schrödinger equation with initial value u0 and the right-hand side f, you can rewrite it using the previous variational principle, okay? But instead of you looking to functions u that belongs to the set xh, you can replace the set xh by the set xh0, okay? First thing. And the set xh0 is given by this formula, and here h0 is just a Laplace operator. So this guy, this semi-group, is much easier to describe. So that's the one with the full operator, okay? And then what you can do is transform these minimization problems by writing u star as being the semi-group exponentials minus ith0 times some function v star, and v star will belong to h1 of I calligraphic h, and this space you fully know what it is. Okay, it's very easy to characterize. And you can rewrite these minimization problems as minimization problems on v star instead of u star. Okay, if you do so, here I'm going a bit quick. You can do calculations. Okay, this is just algebraic manipulation. But in the end, what you obtain is that v star will be the solution of the minimization problems of some function on f defined on h1 of I with values in calligraphic h. So this guy is a space, you perfectly know it. And this f functional is given by this formula here. Okay, this is a quadratic functional in V. And in addition, you perfectly know how you can compare it with the h1 in time with values in h norm. Okay, you got typically this type of inequalities, and here the constants again depend mainly on big T, the finite time interval. And so this is quite convenient. And this is the variational formulations that we are going to use to propose new dynamical low complexity approximations of the solution of the Schrödinger equation. Okay, so this was just a remark. So here I've written this formulation in a general setting for general H0 operators H0 and A, satisfying some assumptions. Okay. Remember, there was this assumption here. Okay. So now, if you come to the specific case of the electronic Schrödinger equations that I've introduced you in the very beginning, all this rewrites in the following way. So again, here, psi is the solution of this problem, where H is the sum of H0 and A. H0 is a Laplace operator, and A is a multiplication operator by this Coulomb potential here. Okay? And here, psi is the solution of this Schrödinger equation with no right-hand side and initial condition psi 0. And so this guy indeed satisfies the assumptions I've told you just before. And this comes from an inequality which reads as follows here. Okay, it's quite complicated, but actually it stems from an inequality which is called the Kato-Yajima inequality. And so once you've got this type of inequality, you can prove that the multiplication operator by the Coulomb potential and the Laplace operator indeed satisfy the conditions I've given you before. And so everything I told you about runs smoothly in the case that I was interested in. And so, if you rewrite the variational formulation, now with these particular operators, it rewrites under the following form. The f functional is given by this formula here. And the v, and you can emphasize the exact solution of the time-dependent Schrödinger's equation. You can rewrite it as follows: exponentials minus it Laplace operator. If you define v star to be this guy, exponentials minus it Laplace times psi, where psi is the solution of the exact time-dependent Schrödinger equation, then V star is the unique minimizer of this functional f defined on the set of functions that are h1 in time and L2 in space. Okay. And you've got the same time of constants. And here in this particular case, we can even improve the upper bound here in terms of dependence in big T, the final time. Okay. So that's a new variational principle that we are going to use. And now I'm going to tell you how we are going to use it to build dynamical low complexity approximations. Okay, which was the final goal of the talk. Okay. So now remember, what I was after was to build a dynamical low complexity approximation of the solution of the time-dependent Schrödinger equation. Okay. So here I will still have sigma, like in the beginning of the talk. This set sigma will be a set of functions of L2 over R3n that can be represented with low complexity. Think about low-rank tensor formats or Gaussian functions. Okay. So now the idea is to build an approximation of psi, which will be denoted by psi tilde, which we'll write under the following form. So it will be equal to the multiplication of the semi-group associated to the Laplace operator times the function v tilde, and that's a function v tilde that I'm going to approximate, and which will be so that v tilde of t will belong to the subset sigma at each time t. Okay. So the psi tilde of t will not belong to sigma, it will be this v tilde of t, these new functions. Okay. And this v tilde in particular, I'm going to take it as the solution of the following minimization problem. So it will be a minimizer of the f functional I've given you before, over the set of functions that are h1 in time, and with values in sigma. Only the subset of low complexity functions, and not anymore into the whole space L2 over R3n functions. Okay. And then you've got the following theorem. If sigma, my low complexity set, is a weakly closed subset of L2 over R3n, of the full Hilbert space calligraphic H, then there always exists at least one solution to this minimization problem. It may not be unique, okay, but there always exists one, and this, whatever the value of the finite time big T, which is an improvement compared to the Dirac-Frenkel variational principle for which you had only local in time existence. Okay. So that's one nice thing. Second nice thing, if you use the inequalities that I've introduced to you before on this f functional, if you evaluate f at the v tilde function, you immediately obtain some certified a posteriori error estimate between the approximation psi tilde, so to compute with this formula here, and the exact solution of the time-dependent Schrödinger equation in the h1 in time, L2 in space norm. Okay, which is nice. Also, you can have some a posteriori error estimators which can help you assess whether your approximation is accurate or not. And also, there was an important thing, which is that the variational principle should be practical when I wanted to construct dynamical low complexity approximations using either low-rank tensor formats or Gaussians. Okay. So let me just go back to the definition of f. Here, what may look scary are this typical semi-group here with the Laplace operator here. But actually, this guy behaves well when you combine it with low-rank tensor formats or with Gaussians. In particular, if you look at this guy, this is actually a pure tensor product of operator. And so if you look at low-rank tensor formats, evaluating this guy on a function belonging to some low-rank tensor format is quite easy to do if you rely on a separation of variable principle. Also, if you use Gaussians, this guy can be easily characterized using Gaussian functions as well. And so you can make computations quite easily. So even if this guy looks a bit scary, it is not that scary when you use it with either low-rank tensor formats or with Gaussians. And that's quite nice. And in particular, when you use Gaussians, a very nice thing is that you can compute this f function analytically up to the time discretization. And so now there is a question that you might ask, okay, very well, why did you do all this work? Is it interesting to use such a complicated variational formulation compared to the Dirac-Frenkel, the classical variational principle? Okay. And so here I'm going to show you some preliminary numerical results in order to illustrate how both this variational principle behave when it comes to building dynamical low complexity approximations. Okay. So here, one first example with low rank tensor formats. Okay. So it will be a very simple numerical example, okay, just to illustrate what's happening here. And more precisely, I'm going to consider here a finite dimensional version of the Schrödinger equation. Okay. Here, I'm going to consider the following Schrödinger equation, where psi is a discretized version of the wave function that I've introduced to you before. Okay. And here, more precisely, this will be a guy of dimension n times n. This small n, you can think here that this guy is a finite dimensional version of the Schrödinger equation where you've got 2 electrons and you've got n degrees of freedom for each space variables to discretize the wave function. So that's the idea. And here I'm going to use this variational principle in order to compute an approximation psi tilde of psi, which will be a rank R approximation. Okay, so in other words, the low complexity set sigma that I'm going to consider will be the set of elements psi tilde that can be, sorry, here this is an n, also this is not an m, this is the same n as here, which will be a product of low rank matrices. And here R will refer as the rank of the low rank decomposition. Okay. Sorry, j'y arrive pas. Okay. So now consider first the exact solution of the original equation, finite dimensional equation. At each time t, one best approximation of psi of t by an element of this sigma low complexity set is given as a rank R truncated singular value decomposition of psi of t. Okay. And here I'm showing to you the values of the different singular values of psi of t as a function of time. T here. So typically in a violet color, you've got the lowest singular value of the matrix psi of t, and so on and so forth. And what you see here is that these different values of the singular values, there are lots of crossings. And for people who are used to low rank approximation techniques, you know that this is the type of nightmare for a Dirac-Frenkel variational principle. Okay. And so this is the type of structure that you have in terms of singular value of this guy. And now on this particular problem, we are comparing the errors that we obtain as a function of R, the rank, okay, in the L infinity in time norm, okay, of the different approximations that we can build for the psi of t. So there are 3 different approximations. There is first in blue the best rank R approximation that is given by the truncated SVD of the exact solution. Okay. So this guy is the best approximation that you can make, that you know for true, but in order to compute it, you need to compute the exact solution of the Schrödinger equation, which you cannot afford in practice. In red, you've got the error given by a dynamical low-rank approximations computed with the Dirac-Frenkel variational principle, the classical variational principle. And in green, you see the error given by our new variational principle. And you see here that the errors are very different when you make R evolve. And in particular, our formulation yields much more accurate approximation. So this comes to a price in the sense that this guy is much costly to compute than the Dirac-Frenkel approximation one. But still in terms of accuracy, for a fixed value of the rank R, you've got a huge gain in this particular setting. Okay. So that was some preliminary numerical tests to highlight to you how different these two dynamical approximations can be using one variational principle or the other in a simplistic setting. Okay. In the poster of Clément on Thursday, so Clément will also talk about what's happening when you use another type of low complexity functions, which are Gaussian functions. And these guys are very much used by quantum chemists, okay, because you can make a lot of computation analytical, including with this new variational principles that I've introduced to you. And so I'm not going to give a lot of details. I'm just going to say that here, when you use such a kind of low complexity Gaussian subset of functions, this variational principle I've given you, you can use it to devise a greedy algorithm in order to compute an approximation of the solution of the Schrödinger equation as a linear combination of Gaussian functions of this type. And so Clément will give more details in his poster on Thursday if you're interested by that. Okay. Just a summary quickly, and then I will stop. So we've got a new space-time variational principle for the time-dependent Schrödinger equation that is valid in particular on the whole space and with potentials with Coulombic singularities. Okay. And so this new variational global space-time formulation is quite nice because actually with it you can see the solution of the time-dependent Schrödinger equation as a solution of Lax-Milgram-like lemma associated to some bilinear forms acting on some functions that depend on time and on the space. And with this new variational formulation, you can construct some dynamical low complexity approximations that are alternatives to the classical Dirac-Frenkel variational approximations. Okay. It has several nice features. So these dynamical low complexity approximations, you can prove that they exist globally in time, whatever the time of the simulations that you consider. You can have some certified a posteriori error estimator for it, which is quite nice also to estimate the errors that you make between the low complexity approximation and the exact solution. And indeed, in some situations, you see that there are huge differences in terms of accuracy between these new dynamical approximations and the classical ones. So this is, even here, for now, we've got only preliminary numerical results and some numerical examples. Well, of course, the perspective here, what would be nice is to try to extend these numerical approaches to deal with real molecules. We're working on that, in particular in collaborations with Loïc Joubert-Doriol, which is a theoretical chemist in Université, Gustave Eiffel. Okay. And there is also an open question related to this new global space-time formulation, which is the following. As I told you, from the physical interpretation of the wave function, the L2 norm of psi of t remains equal to 1 whatever t. Okay. The Dirac-Frenkel variational principle has this nice feature, which is that on the time interval on which this approximation exists, you preserve the L2 norm of the approximation. So you still have this conservation property on the level of the Dirac-Frenkel approximation. This is a property that we lose with our new variational principle. How to recover it one way or another, this is an open question. And with that, I thank you for your attention.
Thanks very much, Virginie. Is there any question in the audience? Yeah, sure, Anthony.
Yeah, thank you, Virginie. Very nice talk. The gap that we see between Dirac-Frenkel and your approach may be due to the fact that in Dirac-Frenkel, the norm you use for the residual is maybe not so natural. And did you try a Dirac-Frenkel on the V after the transformation by the semi-group? You could also apply another Dirac-Frenkel principle to be fair.
Yeah. Actually, sorry, I should have said it. Here in the Dirac-Frenkel, that's a Dirac-Frenkel of the V. Sorry.
Okay.
I'm sorry. This is also a Dirac-Frenkel of the V because somehow you precondition
Yeah.
You have got a good preconditioner, and this is the Dirac-Frenkel.
And on the psi, it's even above. Is it even worse, Dirac-Frenkel on the psi?
We didn't plot it. We only worked on the V here. Sorry for that. So I've talked, but this is on the V. No.
Yeah, maybe another question. Did you check how far the derivative in time is far from the tangent space?
No, we didn't check that. We should, definitely.
Yeah, sure.
Yeah, thank you for the nice stuff. Maybe a naive question. There's at some point you assume weakly closed manifold, subset, and with some tensor formats, at least in the classical sense, there are non-closeness problems. Is it still the case?
Yeah, it depends on which tensor format. For the tensor formats that I've given in the beginning, so the Tucker, the tensor train, the hierarchical Tucker, and so this weak closedness holds. So this is fine. There are some tensor formats which do not satisfy this weak closedness, but the one I listed, they do satisfy this weak closedness. Yeah.
Okay, thanks very much. Any other question? Maybe a final one? Yeah, Albert?
So, I was maybe misled by your title because when we talk, for example, of dynamical adaptivity for low-dimensional problem, we mean that the grid is going to evolve in time, that things are going to change. So that here you fix the format once. Are you not interested in, and would there be an interest that the rank is evolving with time? This is certainly not what you are doing here because you are looking at a space-time formulation, right?
So here you may make the rank evolve, but you will have to keep it, you will not have it time dependent.
Yeah.
What you can do is that, so that's a bit related to what Clément has been doing with the Gaussians. So you can use a greedy algorithm because here you've got a nice quadratic functional to minimize. So in that sense, you can increase the rank, but we have to keep it fixed along the time. And having a dynamic time-dependent rank, with that, it's not obvious.
Okay, thank you. Okay, so let's thank Virginie again. Thanks very much.